All right, good morning, guys. It is coronavirus day one, and we are ready to start integrals. Okay, integrals. That part of calculus is so much bigger than the differentiation part of calculus. So, on into Calc 2, Calc 3, you will be spending a lot of time on working integrals. And so, to introduce this, I want to visit the area and the distance problem. So, this video will cover how to find the area underneath the curve, and we're going to look at distances using a very similar method that we did to finding the area. So first, let's talk about the area problem. Okay. Now, back in geometry, I know you guys had a really good geometry teacher, and so hopefully they talked about how to find the area of, say, a rectangle, which was length times width. Or they said how to find the area of a triangle, which is 1/2 base times height. You know, we might have even done some more complex areas where we had a bunch of different triangles here, and we had to add up the sum of all these areas in order to find the area of that big blue, I don't know what that is, a clam, a top of a clam, I don't know. But what we're going to be looking at this unit in calculus is finding the area underneath the curve. Now, because this line kind of just wiggles around up and down, it's going to be hard to find using just geometry, because we didn't have anything that was just kind of a fluid line like that. Everything that we had went straight across, met at a vertex and went, exception of the circle, which we could easily argue that that's a polygon with an infinite number of sides. So we don't really need any of that if you took time to draw all of it. But what I want to do is I want to jump straight into an area problem. I want to find the area under the curve of a parabola. All right? From the parabola is y equals x squared, so it's just your basic parent function. And I'm just interested in the area between the x values of 0 and 1. So here's what I'm wanting to use. Okay? Now, first thing we have to do is we have to establish how many rectangles we want to use in order to do this. I'm going to use 4 rectangles on this. I think that'll be good. And so my first order of business is going to be divide up this area underneath the curve using 4 rectangles. So since I'm recording this, I got to be a little extra careful, I guess. That should be 4 good rectangles. And what I'm going to do is I'm just going to cap each one of them off. Oh, rectangles are looking rough already. Got a long way to go. But imagine all those are equally spaced. That's the idea I'm trying to get with there. Okay? So if I could somehow find the area of each one of these rectangles and add them up, I would be doing pretty good as far as estimating the area underneath that curve. Now, since all of these rectangles have equal width, and I went all the way to 1, it's not going to be too far of a stretch, I don't think, to call this right here between the second and the third rectangle 1/2. It won't be too far of a stretch to call between 0 and 1/2 1/4, and here to be 3/4. Okay? And so what I want to do now is I am going to introduce some notation, and I'm going to find the area of all 4 of these rectangles. Okay, so I'm just going to color them in something different. That might be easier. So that first green one right there, man, it is small, but it still has an area right there. And so the area of this first green one is going to be, again, it's, what did we say on the last slide? Length times width. And so the distance right here is going to be 1/4. And then I just have to get its height. Its height, well, it came up to right here. Man, that is tough to know what the height is, even without the y-axis labeled. But I know that it shares a point right there at 1/4, the rectangle and this curve. So if I just take this shared point at 1/4 and plug it into my x up here, that has to tell me the y value as to where it lands on the y-axis. And so I'm just going to actually just plug in that x value. I know that's going to be 1/16, so that means that this height of that rectangle has got to be 1/16. Got 1 down, 3 to go. Next one, I'll just color this one in blue. Again, a lot of people will say, well, the width of this one's 1/2. I disagree. The width of this one is still going to be 1/4. Remember, I tried to divvy this up so that everything has a uniform width on it. Where this one's going to be a little different is I'm looking to see where the top of this rectangle meets the curve. And I did not do good at that, but ideally it would be right there. All right? And so I'm needing to know what this height is. Well, that's where 1/2 comes up and meets the line. So it's going to be where I can plug 1/2 in to my function, and that will tell me the y value. So the height of that triangle is 1/2 squared. That makes sense. That'd be like 1/4. That means that this thing comes up to 1/4. Good? I like it. All right, the third one. You kind of see where I'm going with this. I have the same width on all of these. That's going to be good news, and it's going to provide a shortcut when we do it again here in a minute. But I'm running out of room already. Should have started over some. 1/4, again, will be the width. And to get my height, I just go to the top of my rectangle, right here, and that's shared at 3/4. So again, I'm going to plug 3/4 in to my function. And so you can imagine what this last rectangle is going to be. It's going to have a width of 1/4. I'm sorry, I ran out of room. Go to the next line. And then its height that it shares right here comes all the way up from 1. Well, I know it's the 0.11. And good news, whenever I plug in 1 right there for my x value, I get 1 squared, which is 1. And so the notation I'm going to be using on this, you're going to see me say it's going to be R4. The R means I'm using the right endpoints on all of these rectangles to meet up with the line. And then the 4 means that I used 4 rectangles to approximate this area. And so whenever I put all this in my calculator, I get the area is 0.46875. Now, I know that's not the real area. I'm just using approximating methods right now. I'm willing to bet, actually, that is greater than the actual area of this blue region that was originally under the curve, because I have all of this excess space up here on all these rectangles. All right? But it's a good approximation, and we can do a little bit better. Okay? And hopefully we'll do that in this lecture. Man, we made a mess of that graph. Good job, guys. Oh, I didn't want to go to that yet. Oh, definitely didn't want to go to that. All right. So I want to do all this again. Might give you a little bit of leeway on this one. Let's see what you get. But this time, I'm still going to use the 4 rectangles, but I am going to go on the left side. So to show that I'm going on the left side, first I'm going to leave myself enough room, so I'm going to put it over here next to the graph. And so I'm going to use left endpoints. I'm still divvying up all of these regions right here. But the goal is this time the top left corner on all of these will meet up with the original blue function, y equals x squared. All right, and then what I'm going to do is I'm just going to go through and find the area of all of these rectangles now, using the exact same method. Well, I know that the width of all of these is 1/4. That did not change. And it's for the same reason that I had on the last one. It is because this is going to be 1/4. This number will be 1/2. This number will be 3/4. And of course, that's where I landed at 1. Okay? And so to find the left endpoints on this, again, I'm just going to go. I'm going to take it a rectangle at a time. I'm just going to do this first one right here. It has a width of 1/4. But I want to look and see where the top of that rectangle meets my blue line. And that's going to be way over here at 0. So I plug in, still 0 right there. And that makes a lot of sense. 0 squared is 0. And it means that this first rectangle does not have any area. Yeah, it's flat against the axis, so it's not going to have any area. And on the next one, using the same idea, it's got a width of 1/4. but it's going to be this side that meets up with the axis. So the 1/4 squared isn't in the first rectangle this time. It actually is in the second rectangle. And then I can repeat this process all the way down. I'm just going to speed up here a little bit. I'm going to do 1/4 times 1/2 x squared. I still ran out of room. That's how I roll. And then this last one, it's still going to be 1/4 times 3/4 x squared. Now, I'm going to do, let's hit the DHS easy button on this real quick. I see that all of my terms up here have a 1/4 in common. So from now on, you're going to see me pull the width out in front. And I just have to go through and add up all my heights. That'll be a few less buttons to punch into the calculator. All right? And whenever I do punch those buttons into the calculator, I get 0.21875. Now again, that's not a very good estimation because I have a lot of area left over that went unaccounted for on this figure right here. And so I'm really feeling like this area I found, this area came from the inside of all of these rectangles. I'm really feeling like I underdid what the area actually is. And so we can obtain better estimates with this. You can actually average the two areas we get, and that's a really good approximation method, but it still doesn't give you the exact area that's underneath this curve. So let's talk about how to get better and better on this. I could put in more rectangles. Look, whenever I put in more rectangles, this time I used 8 approximating rectangles. Look at the areas down here that are underneath the curve. They're not nearly as big as what they were on the last ones. All right, so if I was to use approximating rectangles, I could probably get a little bit better. All right, what's next? I could use even more. I could use 10. I could use 30. Can you imagine how long it would take to add up 50 rectangles like this? But man, look how closely those 50 rectangles follow that curve. I get a better and better approximation of this the more rectangles I plug in. So I think you know where this is going. I'm wanting to plug in an infinite amount of rectangles underneath that curve. If I could somehow plug an infinite amount of rectangles underneath that curve, I think it will tell me what the best area is, or what the actual area is. Okay, so let's use the same example that we just did. It says I'm using upper approximating rectangles, and it even tells me what the answer is. I'm hoping to get 1/3 right here. Okay, so I'm just going to do a rough sketch of what I just had a while ago. And so I have this parabola that's coming up, and my goal now is, it says I'm using upper approximating. The upper approximating just means I want the rectangles that are, let me switch colors so you can see that better. I want the rectangles that are on top of the curve. So that would be my writing point. So I want an infinite amount of these. I only drew 5. I want an infinite amount of rectangles underneath right there. Okay? Well, if I have an infinite amount, and suppose this is an infinite amount. I obviously know it's not. But it's going from 0 to 1 right there. That means the width of each one, if n is going to approach infinity, and then n is the number of rectangles that I have, then the width of this first one is going to be 1 over n. And the width of the second one, well, where the second one meets is going to be 2 over n. And it's just going to keep going. If you don't believe me, look back at the last example that we just did. And I'm willing to bet I took 1 divided by 4, 4 being the number of rectangles that I had. 1 divided by 4, my first width landed at 1/4. And then I took 2 divided by 4, 1/2. And so it pans out where my width is, all my widths are going to be 1 over n. Well, they'll all just be 1 over n. Okay. And then my heights of all my rectangles, well, that's just where, again, where this right point on top meets the top, or meets the line. So it'd be 1 over n squared. And it would be, 2 over n squared. This is where all of them will land, 3 over n squared. All the way until I get to n over n squared. Remember, n over n, well, that's just 1. So it turned out well for me. Okay? All right, so let's make this happen. Let's see what this math looks like. Okay, so I'm using right endpoints, and I'm using n of them, where n is approaching infinity. We'll get to that in a minute. But the idea is I'm wanting to take the width of the first one times the height of the first rectangle. I'm going to take the width of the second rectangle, add it to multiply it by the height of the second rectangle. Width of the third times the height of the third. I'm just going to keep going until I get to the very last rectangle. Suppose this was the infinite amount of rectangles. This was my nth one. That means that its width is 1 over n, and its height is 1, which is just n over n squared. All right, we can do some algebra with this. Let's just start off, because again, I told you I had that greatest common factor I always wanted to pull out, 1 over n. I see another greatest common factor. I see where I'm going to have an n squared on the bottom of every single one of these terms. So I'm going to go ahead and pull out a 1 over n squared as well. And so what that leaves behind is just going to be 1 squared, plus 2 squared, plus 3 squared, plus all the way up to n squared. Well, the front end of this is simply just going to be 1 over n cubed. And this back end, you're going to have to reach way back into your Algebra 2 days with Mr. Noyes, Mrs. Hill, whoever you had. And you're going to have to pull out, this was a geometric, this is a special series that we had right here, okay? Where the sum of all of these squared, the sum of these squared from 1 to n was n times n plus 1 times, n plus 2 all over 6. More on this in just a minute. All right, but let's just go ahead and plug that in. N times n plus 1. This is 2n plus 1. So times 2n plus 1 all over 6. And again, remember, I'm looking for these right endpoints. Okay, so I'm going to start doing a little bit of calculus now with this. And so that n, I'm going to go ahead and cancel with one of those. I want to work with as little as possible on this. Okay. All right. So I am wanting to use these n's. Remember how many n's I have? I have an infinite amount of them. So I'm actually going to go back to a limit and do the limit as n approaches infinity of this mesh right here. Okay? So I see that on bottom I have 6n squared. And I'm going to go ahead and FOIL the top. The book's going to work a little bit different than I do, but I'm going to try to work it much like we did in class. All right? So I've got n times 2n, times 2n squared. I have n times 1, and which is n, and then add that to 2n, so it's going to be a 3n, and then a plus 1. Now you have to reach way back into your first quarter calculus handbag, and you have to remember that whenever I'm taking the limit as n approaches infinity of a rational function like I have, the way that I handle this is I divide by the highest power that is in the denominator. Every term, I want to divide by n squared. Now, that's going to make some stuff happen. If I have 1 divided by something that is incredibly large squared, it goes to 0. Same thing here. And it leaves me with just taking the limit of 2 over 6. Because the n squareds cancel here. It just leaves me to 2 and 6. And lo and behold, as my Calc 3 professor would say, we get 1/3. And so the actual area underneath this curve right here, if I was to draw an infinite amount of rectangles, would be 1/3. You might have to pause that and go back and watch that again. I did not try to make that look easy by any means, but I did try to cut out some steps to make it all fit on my screen. And the thing is, if I would have done left endpoints on this, I'm saying, oh, well, is the bald guy going to do left endpoints on all this and do all this for left endpoints? I promise you, if I would have done left endpoints on this, my math would have been very similar, and I would have still ended up with 1/3. So once we're showing that n is approaching infinity on these, we're good to do either positive 1/3 or to do left endpoints or to do right endpoints. We'll get the same answer on it. If you don't believe me, I would love to show you. Now, you saw me just kind of just muscle these out right here. Obviously, there's a pattern right here, and so I want to go over this pattern with you as to something that you can use on every problem, okay? Yeah, we made a mess of my board. That's a good thing. That's a good thing. It means we're learning. I hope. Oh, I'll come back up to this in just a minute. I'm going to leave that guy up there, because I'm going to use him again. Willing to bet. All right, so suppose I just have a curve like this. Oh, is that little red dot bothering you? I feel sorry for you guys today. I'm going to go ahead and erase it. I can prove this during our Q&A time if you want me to, but if I'm just looking for the width of an interval, something that would have used on that first example is I can always take b minus a and divide it by n, where b is going to be the end of my interval, and then a is going to be the beginning of my interval, and then n is still the number of strips that I have, okay? And so if I'm looking at right endpoints, I can simply just take my a and add a delta x, where delta x is just the change in x, how much a is changing. So a plus delta x would land me at x1, all right? If I take my a and I add 2 delta x's, 1, 2, it's going to land me at x2. And you can just kind of see how this would go. A plus 3 delta x's, that would just go 1, 2, 3, boom. I landed it at at x sub 3. So that's just some formulas that we may or may not use. We can make more sense of those later if we need to, okay? But what I'm going to look at is I want to look at the actual area of a region. I'm going to formally introduce what I just did on that last example. It says the area A of the region S that lies under the graph of the continuous function f is the limit of the sum of the areas of the approximating rectangles. Whew, man. All right. Let's just put that in mathese up here. That just means that the area is just simply going to be the limit as n approaches infinity of the height of your first one times delta x plus f of x2, or the height of my second approximating rectangle times delta x, my width. So same thing we've been doing. I'm just formally introducing it all the way up to the height of my last approximating rectangle, again, times its width. And we know that we can write this a little bit better. Okay? So we can now say that the limit as n approaches infinity of the sum as I goes from 1 to n, and what we're going to do is we're just going to plug in an f of x sub I on that, just meaning that I is going to be is going to go 1, 2, 3, 4, 5, 6, 7, 8, all the way until it reaches n, times this delta x. Okay? And that's going to be my sigma notation that I use on this, and that's going to take me really far into this chapter. So very important box right here. Okay? Very important box. And we can also do this with left endpoints. I'm going to skip that just for time's sake. Okay. So let's do a new curve, and let's see if we can find the let's see if we can use some of these new formulas. I just put that out there. I don't know what's going on here. Okay, so example 3. I am wanting to find a A is the area under the region of the graph. Y equals e to the negative x. And we don't really have to know what that looks like. We know it's an exponential, and I can definitely draw an exponential. Oops, that has been reflected over the y-axis. So not too hard to figure out what that means. But I want to use right endpoints. I want to find an expression for a as a limit. I want to write this as a, okay? And I'm just going to have this be formula driven. You know where the formulas came from, so you can work it that way, or you can just use the formulas that we know. So part A right here, I'm wanting to use right endpoints. And there's going to be, it doesn't tell me a number of how many to use, so I'm just going to assume that there's going to be infinitely many of them, okay? And so according to my definition, it's just going to be f of x1 times delta x plus f of x2 times delta x plus dot 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 all the way up to f of xn times delta x. He's probably getting excited. He's like, hey, the bald man doesn't have as much screen to use on this one. You're right. This will be a little bit shorter. Okay. And so what does that mean? Well, it means that I'm going to take this x1, and I'm going to plug it in for this x. I'm going to take the x2, and I'm going to plug it in. So that gives me e to the negative x1 times my delta x plus e to the negative x2. Just take this x2 and plug it in times delta x plus all the way up to e to the negative xn times delta x. See if I want to put that delta x on the top. Now, I know what my delta x is going to be. I gave you a formula for delta x a while ago. My delta x is just going to be b minus a over n. So unfortunately on this one, I don't have a fixed one. It's going to be like the last one. The width of each one of these rectangles is going to be 2 over n. So I can plug in 2 over n in for all of these delta x's. Okay. And again, I'm going to use that shortcut where they're all in common. And so if I pull out all of those delta x's, I have 2 over n pulled out in front of all these e to the skip a step. Give me a second. Let me backtrack a little bit. I'm going to pull these 2 over n's down. I thought I was going to skip that step, and I don't think I'm going to be able to. Right, and then I want to rewrite my e to the negative. Well, instead of x1, we said that x1 would just be the 2 over n. So that would just turn into 2 over n. Plus e to the x2. Let me show where these are coming from. Okay? We said that my x1, if I was to draw my graph, would simply be equal to my delta x, 2 over n. My x2, working that out, that would be equal to my x1 plus a delta x, which is 4 over n. My x3, again, I'm just bringing down the previous one and adding a delta x. That'd be 6 over n. You can kind of see a pattern going with this. Like my x sub n, I'm just simply taking whatever my subscript is right here, which is my, I'm just going to call it I, and I'm multiplying it by 2, and then throwing it over n. Okay? And so that would actually be my x sub I interval. And so back over here on this problem, if whenever I'm getting ready to do this e to the negative x2, e to the negative x2, well, my x2 is 4 over n. So it's e to the negative 4 over n times 2 over n plus dot, 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 all the way to the last one, e to the, well, negative x over n. If I was to plug in n for this I just get 2. So it's e to the negative, I'll go and put 2n over n. And that gives me that sum. All right, again, I'm looking for this area. And so it's going to be it's going to be a limit as n approaches infinity. And I'm going to go ahead and pull out all these red 2 over n's. Okay? And so what that leaves me with is all of these e to the negative 2n's plus e to the negative 4 over n's plus all the way up to e to the negative 2n over n. One last step, I can actually shorten this just a little bit into my notation. Got the limit as n approaches infinity. I've got the 2 over n hanging out in front. And then I'm just taking the sum as I goes from 1 to n of e to the negative 2i over n. Just this guy right here. And so that is a long way getting around to what that actually wanted. So part B of this wants me to estimate using midpoints on this. Okay, so let's talk about how to use midpoints on this. Imagine if so it's an endpoint and using 4 subintervals. So I'm not doing the infinite amount on these. Okay, I'm just doing simply n equals 4. Okay, now if n equals 4, that gives me a new delta x I can plug in for. That means my delta x is going to be 2 over n, which will be 2 over 4, which will be 1/2. So starting at 0 right here, I want to make the intervals for my rectangles that I would normally draw. And keep in mind that delta x, the width of each one is going to be 1/2. So the first one's going to go from 0 to, I'm just going to use decimals on this, you'll see why, 0.5. My next rectangle, if I was to draw this out, would go from 0.5. And remember, they're only allowed to have a width of 1, or a point of 1/2, so it would just go to 1. My next one would go from 1 to 1.5. And then my last rectangle, if I was to draw this out like I did earlier in this video, it would be 1.5 to 2. Look what I have. I have 4 stub intervals. Each one's 1/2. And they go from 0 to 2. Okay? And what I can get from this, the reason I wrote this as decimal is because now I can easily get some midpoints from each one. Some people argue midpoints is the best way to go. So the midpoint, halfway between 0 and 1/2, is 1/4. Halfway between 1/2, I said I was going to use decimals here. I am rolling with fractions again. 1/4, 0.25. Halfway between 1/2 and 1 is 0.75. 1.25. Let's say 1.75. And so those will be all of my midpoints. And so whenever I use midpoints on these, I'm going to use an M instead of an L or an R, just so that the teacher that actually did use midpoints. And I'm still wanting to do the same thing on this. I'm wanting to take the height at 0.25 and multiply it by my delta x, which is just 1/2. I'm just going to put delta x for now. I'm going to take the height at 0.75, my next midpoint right here, and multiply it by delta x. I'm going to take the height at 1.25 and multiply it by my delta x. Kind of see where this goes all the way down and around and through. Okay, I'm going to call this my plug and chug step. I'm just going to take this 0.25. Remember, this is where I just come across and I plug it in for x. So same thing we did on the first one. I'm just showing you how to do all this with formulas. If you like drawing everything out, we can definitely go through and draw all this out if we needed to. So I'm going to get e to the negative 0.25. And then my delta x is 1/2. We'll just keep the decimal thing going. I'll put 0.5. And I get e to the negative 0.75 times my delta x is still 0.5. I get e to the negative 1.2, that's not 1.25 times my delta x, 1/2. E to the negative 1.75. And again, you can pull that 1/2 out in front if you want to. But anyway, when you type all this in your calculator, you get this. It's an approximation. Let's throw in my approximation symbol. It's going to be 0.8557. A lot to take in there. Pretty much the difference on this one is that instead of using right endpoints and bringing down this 0.5 right here, I had to go and add another extra step and do midpoints and bring it down. Instead of bringing down 1 down here, I did midpoints and brought this down. Otherwise, it was the same as my first example, and I didn't have to draw my curve on this one. Okay? All right. The distance problem. I was wanting to show you that distance is going to be working very similar to this. Okay? We can find the distance of an object. I still didn't go back and get that. We will talk about this on the last slide. Remind me. Okay? If you don't remind me, I'm going to forget, obviously. So, should you remind me when you're watching this video days after I record it? It says the distance traveled by an object during a certain time period if the velocity of the object is known at all times. I read that wrong. Define the distance traveled by an object during a certain time period if the velocity of the object is known at all times. If the velocity remains constant, then it's easy. It's like driving a car. I can find how far I go by just taking my distance equals rate times time. All right? If I want to know how far I've driven on my way to St. Louis, I just simply take, oh, well, I'm going 60 miles an hour, and I've been in the car for 2 hours so far, so I know I've gone 120 miles. But if the velocity varies, which it often does, it's not as easy to find the distance traveled. But we can use what we did today in this video to help us. All right? So I'm actually going to work one of your problems. Let me get you going on your practice problems on this, okay? Okay, so let's take a look at practice problem number 13 in your book. Okay, it says the speed of a runner increased steadily during the first 3 seconds of a race. Her speed at half-second intervals is given in the table, which I put on the board. I want to find the lower and upper estimates for the distance that she traveled during these 3 seconds. For the distance that she traveled, remember, I had a very easy explanation of d equals r times t to find the distance. Problem is, it's not steady throughout. And so what I'm going to be doing is I'm going to be looking for uppers and lowers. And I can definitely graph and plot all these points, and it would give me a nice curve that's going up because the runner is speeding up. Okay, so I'm gonna use my lower. Okay, I'm gonna do a lower estimate. Now keep in mind, like this would be a rectangle, this would be a rectangle, all the way down. These would be approximating rectangles. So first of all, I can't have 7 of them. I can only have 1, 2, 3, 4, 5, 6. So those would be the bottom of my rectangles going up. And if I'm doing an L6, it means I want to use the left side of each one. 2, 3, 4, 5, 6. This 3 right here is not on the left end of any rectangle. So I'm just going to kind of let it just not be there, okay? Now, it doesn't give me a function on this one. Rather, it tells me what the velocity is going to be. And so using this idea, I can tell you that the velocity of this first one right here, well, it was going to be 0. And again, I'm going to multiply that by the width of my rectangle, 1/2. Add it to, all right, I'm using left endpoints, all right, so the next one's going to be 6.2 is my velocity. And so the best that we can tell is that she went 6.2 feet per second for 1/2 second. The next one is 10.8. The best I can tell using a left endpoint is that she went 10.8 feet per second for, again, 1/2 second for this time period right here. Let me color coordinate this next one in case it's not making sense. So for the next one, where am I at? 1, 2, 3. I got 6 of these to do, all right? Best I can tell, she went 14.9 meters, I keep on saying meters, feet per second for this time length right here of 1/2 second. kind of see the pattern I've developed here. Get the pattern down, and it's not going to be too bad. How many do I have? 1, 2, 3, 4, 5. I have one more to go. All right, so at 2.5 seconds, it's like whatever this function is, they plugged in 2.5 and got 19.4. They already plugged in this 2.5 into my e to the negative x or whatever it is and gave me 19.4. I just have to take the 19.4 and multiply it by 0.5. And so my lowers on this actually gives me 34.7. I'm going to let you play with the uppers on this, the right endpoints. Okay? So the right endpoints, I'm just going to be using the right side of each one of these intervals and then work my way back. So that means I'm probably not going to be using this 0 at all because this 0 is just on the left side of this interval right here. For the right side, I'll be using 6.2. So I'll let you play with that. And it's not 4. That's my bad. I got carried away with 4s from earlier. There's going to be 6 of them again, and you're not going to get 34.7. I'll let you play with that as part of your practice problems, which are, well, which are these right here. Not many of them. I want to go back and touch on this. There's only really 3 things that can happen if you remember when we're adding all this up. I thought we were going to come back to it. I think it's going to be in the next video that we use more of these. But you know how we had an I squared in on that example 2? There's only going to be 3 ways it happens. It's either going to be an I squared or just an I, which gives me n times n plus 1 over 2. Or it's going to be an I cubed in there, which will be n squared times n plus 1 squared over 4. I do not expect these to be memorized. We don't hit hard enough on this in DHS anymore, and so these will be available on the board, on a note card, something whenever you're taking your assessment. Put them on top of your homework sheet that you're writing down these practice problems on.